For decades, the Big Bang Theory has been the widely accepted explanation for the origin of our universe. However, scientists are now beginning to question its accuracy. Recent data and observations suggest that the universe may not have begun exactly as we've been taught. One major challenge is what's known as the lithium problem. Alongside the mystery of the matter-antimatter imbalance, this issue is shaking the foundations of modern cosmology and potentially pointing toward an entirely new understanding of the universe. According to traditional Big Bang theory, the universe began with an enormous expansion from an unimaginably dense point. This view held strong for many years. But now, new discoveries, particularly those made by the James Webb Space Telescope, along with growing dissent in the scientific community, are casting doubt on this long-standing model. At the center of the debate is the lithium problem. The Big Bang Theory predicts a specific amount of light lithium should have formed within the first few minutes of the universe's existence. Yet, when astronomers analyze JWST data, searching for traces of this lithium in some of the oldest stars, they consistently find only a small fraction of what the theory predicts. This inconsistency was known even before JWST's launch, but the latest observations are making the discrepancy harder to ignore. Both the Hubble Space Telescope and various ground-based observatories had already identified ancient stars that, by all accounts, should contain detectable amounts of lithium. But the expected signatures simply aren't there. The numbers don't add up, not even close. The James Webb Space Telescope, JWST, has pushed our view of the cosmos even further back in time, yet, surprisingly, it still hasn't detected any significant concentrations of lithium. So how does this align with our current understanding of the universe? And is the Big Bang Theory still holding up? One possible alternative is the galactic origin of light elements model, or GOL. Unlike the standard theory, which suggests lithium was created in a massive cosmic explosion, GOL proposes that lithium formed gradually within the first generations of stars. These ancient stars are believed to have slowly enriched the universe over millions of years, not just with light, but also with the essential elements needed for life. Another mystery that demands attention is the surface brightness of distant galaxies, as well as the puzzling distribution of matter and antimatter in the universe. This brings us to one of the most profound questions in modern physics, the matter-antimatter imbalance. This issue touches the very core of our existence. Why is there matter at all? Why did the universe form in a way that allowed stars, planets, and life to emerge, instead of everything simply annihilating into pure energy? To explore this, we must first understand matter and antimatter. Matter is made up of fundamental particles, atoms, electrons, protons, and neutrons. Everything with mass and volume, from stars to living beings, is composed of matter. In theory, every particle has a corresponding antiparticle. Electrons have positrons, their positively charged counterparts, protons have antiprotons, and so on. Antiparticles share the same mass as their corresponding particles but carry opposite electric charges. When a particle and its antiparticle meet, they effectively cancel each other out. Scientists describe this as annihilation, a process where both disappear, releasing energy, usually in the form of high-energy radiation. According to the standard model of physics, matter and antimatter should have been produced in equal quantities during the Big Bang. From a physical standpoint, there's no reason one should have been favored over the other. Yet, the universe tells a different story. What we observe around us is almost entirely made of matter. Antimatter, by contrast, is rare and only found under specific conditions, either produced artificially in laboratories or as fleeting components of cosmic rays. No known star, galaxy, or living being is made of antimatter. This brings us to a profound mystery. If matter and antimatter had existed in equal amounts, they would have annihilated each other completely, leaving behind only radiation. In that scenario, no atoms, no structures, no light, nothing, would exist. Yet, we are here. That suggests a slight imbalance occurred after the Big Bang, just enough extra matter, possibly only one particle in a billion, to tip the scale. That tiny surplus is what formed everything we see today, including ourselves. Without it, the universe would have vanished as quickly as it began. But what caused this imbalance? Was it a deliberate act, a cosmic accident, or something else entirely? Physicists point to a phenomenon called CP violation, a break in charge parity symmetry, as a potential explanation. Some particles and their corresponding antiparticles don't behave exactly the same way, a phenomenon observed in experiments, such as the decay of certain mesons. However, these known effects aren't enough to explain why matter overwhelmingly dominates the universe today. This suggests that there must be additional, yet undiscovered processes or particles that subtly tip the cosmic balance in favor of matter. Recent discoveries and unresolved issues in modern physics hint at these unknown and unexplored aspects. Theoretical concepts like baryogenesis and leptogenesis aim to trace the origin of matter-antimatter asymmetry to processes that occurred shortly after the Big Bang. Some other hypotheses propose that in parallel universes, antimatter could be dominant, creating a kind of cosmic equilibrium within the multiverse. However, all of these ideas remain speculative, lacking solid observational evidence. The matter-antimatter imbalance isn't just an unanswered question in particle physics, it represents a fundamental gap in our understanding of how the universe began. Baryogenesis and leptogenesis lie at the heart of this cosmic puzzle. If matter and antimatter were produced in equal amounts during the Big Bang, why is there almost only matter left today? Both theories explore how a tiny imbalance could have emerged. Baryogenesis refers to the processes that produced more baryons, particles like protons and neutrons, in the early universe. The key may lie in CP violation, a phenomenon where matter and antimatter behave slightly differently under certain conditions. If such symmetry violations occurred just after the Big Bang, they could have led to the slight excess of matter we now see. A slight imbalance might have been all it took for a small amount of matter to survive while the rest annihilated with antimatter. This idea is closely linked to a concept known as leptogenesis. Leptons, particles like electrons and neutrinos, play a key role here. According to certain theories, including the seesaw mechanism, extremely massive right-handed neutrinos may have existed in the early universe. These hypothetical particles could have decayed in a way that created a surplus of leptons over antileptons. This imbalance in leptons is believed to have later transformed into a baryon asymmetry, an excess of matter over antimatter. Crucial to this process are interactions called Sphaleron processes, which are fundamental within the standard model of particle physics. While these theoretical models are mathematically sound and could answer many of our deepest questions, they currently lack experimental confirmation. The heavy neutrinos predicted by theory haven't been observed, nor have the new sources of CP violation that would be required. However, ongoing experiments at CERN and the Large Hadron Collider in Geneva are expected to push neutrino research forward in the coming years, potentially resolving these mysteries in particle physics. If successful, we may finally understand how a perfectly balanced Big Bang led to the slight asymmetry that gave rise to everything we know, including us. This also opens the door to even more profound questions. Could there be antimatter universes, dark reflections, or even a mirror universe where antimatter is the dominant form? Though it may sound like science fiction, these are serious considerations in modern theoretical physics. If the Big Bang produced equal amounts of matter and antimatter, where did the antimatter go? Was it annihilated, or does it exist in an alternate reality? One compelling idea is the existence of a mirror universe, a cosmos like ours, with galaxies, stars, and even life, but built entirely from antimatter. In this scenario, The universe may have split into two separate realms following the Big Bang, one made of matter, our universe, and the other composed of antimatter.